Now, how can we prune these branches? We start here. We're doing a depth first traversal. We're going to go here next. We're going to go here. We're going to go here. And we're going to go here. The first time we reach our depth and we evaluate the state of the game, we get a 5. Okay? So here we are. We get a 5. Do we like that state? We have no idea if we like it or not. This is the first thing we've ever seen. This is a 5. And we know at that moment that we can get a 5 if we want to. Well, this is the maximizing agent, right? And the caller is the minimizing agent. So is the caller going to choose that 5? We don't know. It depends on what the next one is. So should the caller recurse into this node? Yes. Well, now we have a 5 and a 6. Which one is this caller going to choose? The 5. Therefore, the utility of this state is a 5. So on the return, we've kind of figured out the value of the state. And now this node knows, if you get to me, I can get you 5 units of utility. We know this knows it can get a 5. It returns 5 to its parent. And so far, this node knows, hey, I can get a 5. Should this node check its child on the right? Well, the answer is yes, because it might be better than a 5, right? So we go down here, and this node checks here, and we get a 7. So this node at this moment says, hey, I can get a 7. But should I check this one? Yes, because it might be lower than a 7. And as the minimizer, I really want something lower than a 7. So I'm going to check here. Turns out it's a 4. This node knows it has a utility of 4. And now should this node check its right child? Now you're all saying no because you see these little 2 red crosshatches. But can you see why we can now say the Eeyore line? Why bother? They'd never pick me anyway. Imagine, so we know this node has a 4, right? What if, pretend you can't see that 5 there. What if it were 1,000? Would this node go with it? No, we'd stick with a 4 because I'm the minimizer. Okay, what if it were a 0? Would this node pick it? Well, yeah, but this node knows that its parent is the maximizer, right? And because this node knows that its parent is the maximizer, and its parent has already seen a 5, and it can already get a 4, this node already knows it's not going to be picked. It's too good, right? It's too good for the minimizer, too bad for the maximizer. We already know as soon as we found that 4. We didn't know when we found the 7, because there was a chance that if the 7 was the smallest we could get, that the maximizer would choose this one. But once we found that 4, the minimizer says, hey, wait a minute, I'm so good that I'm worthless. My parent is never going to pick me, therefore I might as well just quit now. Why bother? They'll never choose me anyway. And so we don't even bother anymore. We just return, yeah, I got a 4, and this one ignores it. And this node says I got a 5. Okay, so we come up here to this. Come up here. This node doesn't know what it's got yet, but he knows I can at least get a 5. Should we go down here? Yeah, because it might be smaller than a 5, right? What if that were a 0? It could be. So we go down here, and it could be better, and we could check, and it goes all the way up. Okay? At this moment, the root node knows it can get at least a 3. And as the maximizer, it wants better than a 3. Should it keep looking? Yes. So we go down here, and we say, hey, we can get a 6. At this moment, by the time we've checked this one, we already know that this left branch that's going to go to the 3 will never be picked, right? Because this node knows it can get a 6 by going down this way. Let's get all the way down to this moment when we're right here at this 6. We know at this moment that its parent knows it can get a 6 by going this way. Is there any possible way it would take its right child, knowing that its right child can also get a 6? The circle node that I'm by right now would only accept something better than a 6, right? But if I got something better than a 6, the parent node, the square, wouldn't pick it. Do you agree? So this node at this moment can say the line, why bother? They'd never pick me anyway. And that's how we know that we can prune it. How do we know at this moment that we don't have to do any more work? Because we already got a 5, and the maximizer can get a 6 with this guy. So 5, what's the point? I could keep improving, but it's only going to make me less likely to be chosen. Clearly, this unit can quit right here. Why couldn't this unit quit before it went down the left branch? Because it didn't know. Maybe it was something that the maximizer would have picked. Maybe it was a 7. And so it still would have had to check. Okay. That's how alpha beta pruning works at a high level. You need to be able to do that in your head because this makes a really easy test question. Here's a tree. Which branches will be pruned? Then you prune some, and then I check if they're right and mark points, right? So make sure you can do that. But next I want you to understand how this translates to the differences in this pseudocode. Here's the alpha beta pruning pseudocode. Just for comparison's sake, let's find the actual differences between these two algorithms. The difference is alpha beta pruning has these two variables named alpha and beta, or two parameters, excuse me. These are Greek letters. This is a Greek letter alpha. It looks a lot like the letter A. This is the Greek letter beta. It looks a lot like a B, or an SZ if you speak German. So the point of alpha and beta are they maintain not just the, they maintain some information not just from what you're looking at from the node's perspective, but they come from the parent. So you see how right here we're passing, when we recurse, we're passing alpha and beta to the child node, to the recursive instance, and it uses alpha during its computation of the maximum. So it's basically computing. We're trying to answer that question of, should we bother? Would my parent still have a chance of choosing me? Now look at this condition right here. If alpha is greater than or equal to beta. So what we're saying here is, I'm the maximizing player. That assumes that my parent is the minimizing player, right? So if alpha is greater than or equal to beta, where alpha is the one that I just updated, we're saying if my best move is greater than what the parent would accept. So think of alpha as the best you can do, and beta as being what your parent would accept. Comparing those two checks the condition of, is it worth bothering? Can you see that at least at an intuitive level? Well then, checking that condition, is it worth bothering, tells us whether or not to break. Okay? If it's not, if what you can do is so great that you'd never be chosen, then we might as well just quit now. Stop looking for any better child nodes because the parent would never choose us anyway, and now we can do minimax while not bothering to search branches that don't have a chance. That's it. That's the whole algorithm. You kind of just need to think really deeply about alpha and beta for a while and see how it passes these values in recursion. And that implements the same thing we described right here, where if checking a node would just waste your time because it would only make you better and you're already so good that the parent would never choose you, then you don't need to do it. You'll implement that algorithm, you'll plug it into chess, you'll use a heuristic. Let's suppose you've implemented chess and it doesn't work. What do? Yeah, you want to find out, is your alpha beta pruning working? So plug it into tic-tac-toe, see if it works. What if it doesn't? What do? Fix it, yeah, sure. How many actual boards are there in tic-tac-toe, even? If you start from the beginning and just start stepping through, recursing all the way, there's 9 times 8 times 7 times 6. Basically, it's 9 factorial boards, right? Nope, there's 9 places the first player can go, no matter what, no matter who goes first. So there will be 8 places the second player can go. There will be 362,000 possible tic-tac-toe games that you will play every time you make the first move, just to see what is the most intelligent first move. That's more than you really want to step through, isn't it? Okay, so what you really want to do is you want to find a repro that happens in the last 2 or 3 moves if you can, because, 3 factorial is a whole lot less than 9 factorial. So try, if you can, to fill up the board with random moves or hard-coded moves or something, and then find a case that still fails. If you can, great, your debugging life is easy. You'll step through it and you'll find when it makes the mistake, and that shouldn't be too hard. By the way, get out some paper, play tic-tac-toe, see what is the intelligent move. And if it makes any move that's unintelligent, you found a bug. Because you know what's intelligent in tic-tac-toe, right? Okay. If you really can't find a repro case that unless it requires a lot of moves, then I kind of recommend you write a program that's going to systematically try them all searching for a repro case, because you really want one that's easy to debug. There will be no case where it works, where a bug only shows up in the last 7 moves, because if it did, then the whole minimax concept is broken, right? Either the minimax only considers the level you're at and the children. Alpha beta pruning considers 3 levels: your parent, the one you're at, and your children. So if the bug doesn't incorporate just those 3, then it's not a bug in the algorithm anyway. It's something else. Okay, so you should be able to debug it no matter what happens. The hardest thing is just getting students to actually step in and start looking at it in a debugger, but sometimes you got to do it. A good way to test your chess implementation is we're going to implement it so that you specify as a command line parameter how many moves it looks ahead. And if player 1 is looking ahead 3 moves and player 2 is looking ahead 5 moves, who's going to win? The one that looks ahead 5 moves. So simply by playing with those numbers, if the one that looks farther ahead always wins, or usually wins, that's enough. You can say, hey, I think it's probably right. We'll probably also test it against Scholar's Mate. That's a really simple one to check. If your chess player can't handle a Scholar's Mate attack, you didn't implement it right. If you don't know what Scholar's Mate is, look it up. It's a 4-move checkmate, and it's really easy to do. What if your chess player is too hard? So you play chess against it and it creams you every time. That stinks, doesn't it? Yeah, it's awesome. But what do you do about it? You can always look ahead less far, right? But I find that when I look ahead 2 moves, it's too easy, and when I look ahead 3 moves, it's too hard. So how could you make that a little better? Yeah, I say, yeah, just randomly prune some branches or something like that. I think that's very human-like, because humans are really bad at systematically searching the whole space. One other detail I wanted to throw out there is with the heuristic. Notice I added a random number to the heuristic right there. The reason I did that is it adds just a little bit of non-arbitrariness. Every once in a while, you'll get games where the 2 opponents decide to move their castles back and forth in the background, and it just gets really dumb. By injecting this tiny amount of randomness, that will allow the heuristic will cause it to play some unique games, and it shouldn't really affect the outcome in the end. And that's also why I made my heuristic numbers bigger than the standard ones, is I didn't want this random number to affect it much.